much, Willie. Let me get my screen going. Can we see that?
Yeah.
Okay, welcome everybody. I'm going to be talking on Fynbos and fire. And before I do, I would just like to recommend that those of you who missed Natasha Governor's talk on fire in Kruger, that perhaps you should go and have a look at it. It was a very interesting talk. I'll give the link at the end. And then your homework for this weekend is to see William Bond's video on trees and grasslands. It's really fun, worthwhile. And I see them as background to the talk I'll be giving. You know, I was hoping to talk on Fynbos and fire, a manager's nightmare, but the organizers were a bit too worried I'd get the park manager and the fire manager in Table Mountain upset, because I do tend to be controversial. And so I'm going to concentrate a little bit more on the plants and a little bit less on the management implications and problems. So there's a ghost talk behind this talk I'm going to give, and I hope I don't stray too much from this talk. Okay, now we've been seeing in the news, fires are in the news for the last 3 years. The headlines are getting more and more spectacular. The fires are catastrophic. And here we have one from Europe, and it started off in Portugal and then France. It's been in Italy, and the latest in the news is Greece. And at the same time, we're having fires in Australia, in Sydney, Perth. California has been having fires for the last 3-4 years, spectacular fires, really eye-catching stuff. And Algeria, Tunisia is currently in the news with its fires. So around the world, we're having fires, and those are all the Mediterranean regions, but the fires aren't confined to the Mediterranean regions. So Canada is now coming into the fires as well. And Russia is battling with catastrophic fires, and it's due to, it says, due to lack of fire defense funding. Okay, we all know the fires from Cape Town. We've all been and seen them. 2000 was our big fire on the Cape Peninsula. And then exactly 15 years later, which is the average fire interval, we had the 2015 fire. And I can confidently invite you to the 2030 fire, and hopefully we'll be prepared for it, and we'll be able to sit back and watch the spectacle as it unfolds. And it might be a bit out, it might be 2029 or it might be 2030, but as sure as you've got a nose on the end of your face, there's going to be another fire in 15 years' time. And then in 2017, we had the Great Neisner fires, and it's quite interesting to look at the news headlines. We're now talking about perfect infernos and perfect storms, and the whole of the garden route was burning down. And that's an interesting fire because it started here as a lightning strike, according to one of the theories. It started as a lightning fire, and the teams who went to go and put it out couldn't find it. They couldn't get to it, and they couldn't figure out where it was. And then after about a week, overnight, it exploded, and then within a couple of hours, 2 houses were down, a family was dead, and then it roared across the area towards Neisner. But it wasn't the only fire. Under those conditions, a few other fires, at least 2 other fires broke out simultaneously. And then more recently, we've just had our Easter fire on Devil's Peak. It might have been started by vagrants, and it burnt towards UCT, spectacular fire. And just some pictures from UCT News. Look at that tree. It's all on its own. There's no fire around it. It just decided to burn on its own. Some species carry fire, some species are dangerous, and these are not the plants you want to have around your university or your house. UCT should not have been unprepared because the botany department had produced a report about 5 years ago saying that the alien plants were bad and they needed controlling. And unfortunately, the botany department suffered the brunt of it, of some of the fires. A palm tree, not this one behind it, caught fire, and it put embers onto the roof and set fire to the IPC. Or for those of you older, it was the old Percy Fitzpatrick Institute. That's where I got my PhD, and that burnt down in the fire. So that was a devastating fire. It's been our most recent fire. And if you want to just go see why it was so devastating, there is an opinion piece produced by Alana and Karen from Stellenbosch University at the Friends of Tokai Park website, and you can read that if you want just a quick synopsis of what I'm going to be talking about for the first half of my talk. Okay, what do we need for a fire? Well, it's quite simple. We need three things. We need an ignition, we need some oxygen, and we need some fuel. The ignition can come from lightning or rock falls, but most fires are now caused by people. They have for the past 100,000 years. So people fires are part of Fynbos. Yes, there's more people around now, but people have been part of the problem, well, not the problem, part of the fire in Fynbos for as long as Fynbos has been recorded. And then there's infrastructure as well. So things like electric power lines, electric lines, when they fall down, they start fires as well. So these are the causes of fire. But for fire to happen, we need oxygen. Now, the Earth's oxygen is a constant at 21%, and it's been like that for a fairly long time. In the Devonian, it got up to 30%, and that's when we had the dragonflies as big as people, 2 meters across the wingspans. And under the conditions of 30 degrees, all you have to do is bang two sticks together and you've got a fire. So fortunately, we're not living under high oxygen levels anymore, but we do have weather, such as temperature, humidity, and wind, which bring oxygen to the fire and get the fire to burn. Temperature, we have a Q10 of 2, which means that for every 10 degrees, the fire will burn twice as fiercely. So in a cold, high-felt winter, if a fire goes at 10 degrees, it'll burn with a certain ferocity. But if the fire was 20 degrees, it would burn twice as fiercely. And 30 degrees, it would burn 4 times as fiercely. In 40 degrees, it would be 8 times as fiercely. And if the temperature gets up into the high 40s, near 50s, we're talking about 16 times as fierce as it would on a cold, high-felt morning. So the temperature is crucial for the actual ferocity of the fire and how bad it is. But temperature is not nearly as important as humidity. The humidity is actually what drives the fire weather. And we see that if we look at most of South Africa, which gets summer rain, it's hot, it's wet, the plants grow like mad. They absolutely love it. Hot, wet is ideal for plant growth. And then we have the cold, dry winters, and that's when we have the fire season with the cold, dry winters. So in the high veld, in the low veld, your fires are going to be in winter. But that's not the case in the Cape. In the Cape, we have cold, wet winters. So the plants try and grow, and they do okay. They do fantastically under the situation. But then summer comes along, and it's hot and dry, and they can't grow. There's no water. There's nothing they can do. They just have to go into dormancy and wait for the rains to come again. So that's ideal weather for fires. That's exactly what fires want. Nice, hot, dry, and they take off, and it's ideal for them. And that's the reason why it's no surprise that the Mediterranean regions of the world have some of the most spectacular fires that we are seeing in the newspapers. And then, of course, the last thing we need is fuel. The fuel is perhaps one of the most important things, because if there's no fuel, it's not going to burn. And the fuel is determined by the vegetation type. So your grass veld with their fine grasses, that's going to burn much more easy than the fynbos, which is slightly more shrubby. And your forests are going to have a hard time burning. They will burn, but much harder time burning because they've got thick branches which don't burn so well. And then veld age is important. The younger the veld, the less fuel there is. The older the veld, the more fuel. So as we allow the veld to age, so the fuel accumulates and we can get better fires, bigger fires. And then there's some plant strategies. I showed you that plant that wanted to burn. Some plants promote fire. And if you've got lots of them in your environment, you're going to have more fires. And then alien plants. Alien plants tend to come from other regions which are prone to fire. So they're fire adapted as well, but they don't have any of their pests here. So they grow faster, they grow bigger, they produce more fuel, they produce more biomass faster. And as a consequence, they create a higher fuel load and they burn much better and hotter. And then lastly, a way of accumulating fuel is to exclude fire. Okay, so now we're faced with a manager. We've got this problem. We know that there's fires. How do we solve it? Well, the obvious solution is to go for the ignition. Let's stop the fires. If we stop the fires, then we've got no problem with this. There's no fires. End of problem. And so we can throw some resources at it. People, manpower, equipment, money, and we can stop the fires. But as we stop the fires, the vegetation gets older and the plants continue growing and the fuel increases. But that's easily solved. We throw some more money at it. We throw more resources at it. We put more people in and we control the fires. And of course, the fuel increases. You can see where this is going. No matter how much money you put in, no matter how much resources you put in, no matter what you try and do, your fuel will increase until one day the weather will contrive to create a situation where you won't be able to put out the fire. And then you are going to have a catastrophic fire. And how catastrophic will depend on how much money you spent and how much resources you've got and how many firefighters you have and what the equipment is that you're using to control the fire. And the big catastrophic fires that we're seeing now aren't due to the weather. Don't blame the weather. It's due to the fact that people, firefighters, managers, are putting out the fires instead of letting them burn. So under these conditions, a day will happen when it'll be hot and humid and windy enough, and the fuel that's been accumulated will burn, and we'll have a problem. Now, we're humans. We concentrate on the ignition. We need to concentrate on the ignition because we want to blame someone. So if there's a fire, we need to get money. And to get money, we have to say we put out 3,000 fires on the Cape Peninsula last year. So we need more money. And then if something burns down or there's a problem, we need to find someone that we can sue and get them to cover the costs. So the emphasis on managers, on stuff, is actually on the ignition event and what is happening around the fire. From the ecology point of view, the ignition is irrelevant. If we have our little patch of Fynbos over here, almost all the fires are going to start somewhere else. It might be a kilometer away or 10 kilometers away or 400 kilometers away. And the fire is going to move through into our patch, burn us down, and then move out of our patch and continue off in the other direction. So from the patch of Fynbos here on Table Mountain, how the fire started and where it started is irrelevant. All that patch needs to know is that it's going to burn every 15 years, and then it's got to adapt to the fact that it's going to be burning every 15 years. So the Fynbos doesn't worry about ignition at all. It's all about the fuel load, and it's the fuel load that determines the fire return interval if you don't do anything. And if you want to manage fires, the clever way is to manage the fuel and to not ignore the ignition, but to not place so much emphasis on stopping ignition. If you keep the fuel levels low, then you can keep the fire under manageable levels. So what we really want is a situation like this, where you come along and you get your equipment ready and you get your teams ready and you put in your fire belts. And when you're ready with the right weather conditions, the right wind, the right temperature, the right humidity, you light the fire and you start this fire. Okay, some people call this a controlled fire. There's no such thing. The moment you light it, it's out of control. So I prefer the term prescribed burn. And then some people use a fuel reduction burn. If it's a fuel reduction burn, it means you've done something wrong. You want to work with the ecology, you want to work with nature, you want to use fire to fight fire. And this is the sort of situation you as a manager want to be dealing with. Whereas if you keep on putting out fire, fire will choose the conditions, and you'll end up with a situation where you have high fuel loads, impossible weather conditions with high temperature and high winds. Half your team has got to scramble to get there. The other half of your firefighting team has got to go there to evacuate the people you need to move out of the area because their houses are going to burn down. The other half of your team is running to get backwards because the fire has jumped over their heads and then they now need to regroup behind. Whereas a portion of your team is desperately trying to run and survive because the fire is about to overwhelm them and perhaps kill them. These are not the conditions you want to be fighting a fire in. And if you are going to play the game of stopping ignition, these are the conditions that are going to happen because sooner or later the weather will contrive to overwhelm you and take over the situation. And this is not where we want to be. This is not a healthy situation. Okay, I just want to go and do a little bit of history and just how did we get here? And this is just my garden. You can see here it was at a lovely stage at this stage. And as it grew older, it needed a fire, but my wife wouldn't allow me to burn. So I'm still upset that I wasn't allowed to burn my garden. but yeah, it's coming away again. Okay, so let's just go back. 1400s, the Portuguese sailing past recorded that there were great fires inland around the Plettenberg Bay area, but they never landed, they just went on. In Van Riebeck, if you read his diaries, he talks about looking out over what is now the city bowl and seeing the koi fires, their cooking fires at night, dotting the whole landscape. And the koi used fire extensively. When they moved in with their cattle, they would graze, and when they were finished, they set fire to the veldt, and then they migrated on, and then they came back a year or two later and grazed again. So they used fire as the tool for grazing. And they used it for more than that. So one of the expeditions, one of some Van Sel's expeditions up country, the guys discovered that there was no fuel for their vehicles. They were driving by ox wagon with oxes, and they came and the veldt was burnt. And there was warfare between two Khoi tribes. And what the Khoi did was simply burnt the other tribe out by burning before the grazing season. And then there was no food, and the other tribe had to either move, or because the cattle were wealth, and they had to become hunter-gatherers and lost their power and status in the community. So fire was used more than just for refreshing the veldt. It was also used for war. And then in the 1700s, we had the note that Renosterveld changed. Now, we don't know why it changed. It could have been because we were coming out of the Little Ice Age. Remember, Van Riebeck landed in the middle of the Little Ice Age, and things were warming up, global warming. But Renosterveld changed from a grassland to a shrubland. And the current theory is that what had happened was that the Khoi would graze and then burn and then move off and allow the veldt to recover and then come back the next year, whereas your settlers stayed put in one spot and they lit the fire, burnt the veldt, rejuvenated the grass, but then grazed it straight away, and that grazing eliminated the grasses, and so Renosterveld changed from the grassland to the shrubland. And then there was the Great Fire of 1869. In 1869, at sunrise on Tuesday, the 9th of February, 1969, we had a berg wind. A berg wind is a katabatic wind. Those of you in the Cape know it. It comes before every cold front, and it's due to air coming off the plateau. And as it goes down off the plateau, it warms up and dries out. So it's a hot, dry wind. And so it's got all the elements you want for fire. Hot, dry, windy. Perfect. And this was the hottest berg wind in living memory. This intensely hot hurricane raged through an area from Riversdale to Uitenhage and even as far as Port Elizabeth. And fires broke out across a distance of over 450 kilometers, and it seemed like the world went up in flames. So a third of the Western Cape province burnt down in one fire over a couple of days. Okay, now that's a spectacular fire. Reports from the different places say that all the fires started early on Tuesday morning, and this suggests that it couldn't have been a single fire, but lots of fires spreading from west to east in forest, Fynbos, and farms. And of course, this is the situation with weather climate, fire climate. You don't just get one fire when the weather conditions are bad, you get many. And this spread from the mountains towards the coast, all driven by the berg wind, which blows from north or northwest. So a third of the province burnt down in this catastrophic fire. And we thought that the Devil's Peak fire was bad. And interestingly, as we come into the 20th century, the first Cape botanists at the college and the UCT were all anti-fire. So Harry Bolus in 1908 writes, in dealing with the Cape plants, the rarity of some of these is doubtless due to the frequent bushfires. I believe hundreds of species have become extinct from this cause during the last century. And that's weird coming from this guy because he was an orchid specialist. Most of these species flower in the year after fire. And yet he had this view that fires were bad. Rudolf Marlos, who's probably the greatest naturalist we've had in South Africa so far, he wrote, whole hill slopes being sometimes covered with Watsonia and other tall flower spikes, which is spectacular. It's a sad spectacle. And it realizes the tremendous slaughter that has taken place to produce this display. So to get pretty flowers, you need a massive slaughter, and that's sad. Robert Adamson, who wrote Adamson and Salt of the Floor of the Cape Peninsula, he records, by far the most effective agent of change has been the frequent burning of the vegetation, resulting in the retrogression of the normal succession and an impoverishment of the flora. So we're losing stuff because of these fires. And even John Acox, who did the vegetation types of South Africa, he recorded half of the fynbos as false machia, which was derived from natural forest or grassland by burning, overgrazing, and clearing. So he categorized half of our fynbos as being degenerate. Now, how on earth could these guys have had this viewpoint? I mean, these are our top scientists at the turn of the last century, and they are anti-fire. And at this stage, I'm going to move on to the plants. If you want to read up more about this and find out more about this, I can highly recommend Simon Pooley's book on Burning Table Mountain. It's a good read, get hold of it, and you can go and explore the further history over there. So why were these guys so wrong? And part of the reason was because of John Bewes. Now, Bewes was one of the international botanists. He worked in South Africa, but he was one of the people who was instrumental in the whole finding of ecology as we understand it. And he adopted the Clemensian succession idea, which basically said that if you had a disturbance, some plants came in and they colonized the disturbed area, and they produced more nitrogen and they produced more carbon and they improved the soil. And by improving the environment, they made the veld suitable for other species to come in, which also improved the environment and made it better with more nutrients and more thing, and so on and so on and so on, until we came to a climax community, which was a lovely tree community where the soils were highly productive, the biodiversity was high, and everything was happening. And it was this climax community which was the one that we would get most benefit from, and that the environment was striving towards. And this applied in terms of numbers and cover. So the numbers of plants increased and decreased, and the cover of them increased and decreased as the succession moved along through time towards this climax community. Now, how on earth could our botanists, who were keen observers and knew their plants backwards, how could they have adopted this when it's so wrong? This works fine in Europe, but not over here. And part of the problem is that if we look at fynbos, it has the same appearance. If you go and walk in it, the cover shows the same patterns. We start off with our bulbs and our Watsonias and their spectacular displays, which are a sad reminder of the destruction that had to take place in the fire. And then we move to the Restias and the Ericas and the Proteas as the veld gets older through time. So we do have that same succession there, but that is not the story, the complete story, and that's where they missed out by having this European paradigm. So after a fire, the resprouters recover first. We can see some of them flower straight away within a year or two, within 6 months of the fire. And a king protea, our national flower, that's one of the resprouters that resprouts after fire, and they grow fast and recover very quickly. Then come in the bulbs, our spectacular orchids, some of which only flower in the year after fire, and the other species that come in and flower and set seed. And interestingly, a lot of them produce seed which are recalcitrant. That means they cannot be stored. So those seeds have to germinate and they have to grow in this new environment and post-fire. And they, of course, will grow slowly, so they won't flower until the next fire. And these plants will also, having flowered and set seed, they will then disappear, and you'll only see them in the next fire in 15 years' time. And then we have these mass bulb displays there. We can see them. Notice in between, there's not enough fuel yet to carry a fire, but we've got beautiful displays that we'll only see post-fire in that disturbed and desecrated environment that Rupert Marloff told us about. And then the restioids start growing up and start dominating. And it's at this stage when the restias are dominating at about 3 to 4 years after the fire that fynbos can again carry a fire. There's now enough fuel for it to burn. And if a fire does start under ideal weather conditions, it will burn. And as the veld matures, so our other species start coming through, our daisies and our ericas, and we go through to the ericoid fynbos phase, where the ericas are dominating the landscape, and the restias are now being overwhelmed by other species. and the succession continues. Let's just deal with the ericas quickly. Ericas have a wide variety of strategies. It's our biggest genus. And we have species like Erica coccinea, which is killed by fire. Species like Erica mimosa and Erica ceranthoides, the fire heath, that flower after the fire and recoppice from their rootstocks. And then we've got species like Erica siciliflora, which stores the seeds, shown there, that's the seed pod. It's storing the seeds, it's waiting for the fire. And when the fire comes, it will release the seeds. And then we've got fire avoiders, like the gooseberry heath. And it occurs in rocky outcrops where it's relatively protected from fires and where it can grow to 2-3 times the fire cycle and survive the fires. And Erica pattersonii, which is a fireweed, it grows like mad after a fire. It produces its seeds at 2 to 3 years, and by 5 years it's gone. You won't see it again until you come back from the next fire. So within the genus, we have a full range of all the strategies for surviving fire and maintaining fire. And then we have our fire weeds. I've given you examples here from Proteus. These are 2 of the species which we are going to be looking at in a little bit more detail in a little while. And these are the ones which flower quickly, set seed, and die. And then we go into the mature Fynbos phases. These are the Proteus. They dominate. They come into the overstory. They take over the felt, shade out the other resprouters and stuff, and grow on to become the overstory. And at this stage, the Fynbos is ready to burn. And there's just some elements of our Proteus, a whole wide variety of species that make up the Fynbos. Now, Fynbos must burn. How do we know this? How do we know that Fynbos must burn? Well, the story starts, if you like, with Mari Fuchs being called in because forestry was having a problem with the blushing bride. Forestry was looking after the water catchments. Blushing bride had made headlines because it had been rediscovered and was growing in Kirstenbosch, and the plants were doing fantastically in Kirstenbosch, but in the wild, they were all dying out and they were getting less and less. So the forestry called in Mari Fuchs, who was busy doing her PhD on the king protea, and they asked her for advice, and they came here and they did all the usual things, fencing it, keeping out pickers from picking the flowers, and looking after the veld, and it made no difference. Plants got less and less, and was just down to a handful of plants. And then the fire came through, and there were thousands, but the time wasn't right. The penny didn't drop. Nobody realized at this stage that this was a fireweed and that it needed fire. 10 years later, in the 1970s, the same situation arose with the marsh rose. This is the marsh rose growing in Kuchelberg, forestry looking after it, and they had the same issues. They were dying out. Now, I think to appreciate this plant, you need to know that at about 10, 15 years old, most of the plants are dead, but the survivors are standing 3-4 meters tall. You don't look at a marsh rose, you look up to it. And it's absolutely spectacular. And Charlie Boucher came and he looked at the problem, and they tackled it the same way they always did. They fenced it off. They kept out the pickers. They put security guards on to look at it. They looked after it, made sure it wasn't disturbed, and they got less and less and less. And then on June 1979, they were down to the last plant. The species was on the verge of extinction. And there we can see the fences to fence off the population. And notice that this plant is in the fence line. It came up when they scuffled the fence line. All the plants inside are already dead. So the last plant was one of the ones that came up because of the disturbance. And that was it. It was recorded for posterity. And then in January the next year, a major fire came through. And of the 6 known populations, all of them recovered. And we had 3,000 plants growing, and the penny dropped. Fynbos must burn. It's as simple as that. You don't burn it, it all dies and disappears and doesn't survive. So what was wrong with the Clemensian succession that went over there? Remember, we saw that with the cover, it seemed to be showing the same pattern. But if we look at numbers, the Clemensian numbers consist of these different communities which come in, and their numbers go up together with the cover, and they get replaced. That's not what happens in Fynbos. In Fynbos, when we have the fire, everything germinates, and all the numbers are high, And from then on, the numbers continue going down, and there's no species that come in later in the system. They're all there after the fire event. So whereas these European communities that all the scientists and stuff who studied in Oxford and Cambridge and came to South Africa to teach us, they knew the system in which the plants were striving towards a climax vegetation, in which productivity was high and everything was high. But in Fynbos, the plants are living to die. They are living, and at this stage, they want to burn so that this whole system can get going again. Whole fire, the whole Fynbos system is not geared towards the climax, it's geared towards the fire. This is not a catastrophe. This is a rebirth. This is a rejuvenation like Phoenix. You have to burn and become ashes and rise from the ashes. If you want to reborn, you have to die. And if you ask anyone, any botanist who wants to go in the Fynbos, and you say, we're going to certain areas, the first question they'll ask you is, how old is the veld? Because if they want orchids, they're going to come to 1-year-old veld. And if they want proteas, they're not going to not bother until it's at least 5-6 years old. And then they'll go into the veld that's older. So depending on what you're interested in, you'll go to different age veld. And why do we need fire? Well, we don't know, but what the early botanists missed is that there's no recruitment between fires. There are no babies. All the babies come up after the fire. We don't quite understand why this is. One of it is that perhaps there's too little water in summer. So after a fire, everyone germinates, you're on a grand footing. But if you try germinating in old veld, you're competing with all the old guys who've got access to the water, and you're going to die of lack of water. Or perhaps it's a shade thing, or perhaps it's parasites and pathogens. The great thing about fire is that it wipes out all your pests, all your predators, all your fungi, all the hokas that are going to eat you. They've got to come back in again. So it might just be a way of getting rid of those. And if you try growing in old veld, the parasites and pathogens are going to get to you and chew you up. But we know that we can expect fires in Fynbos because of the fuel every 10 to 25 years, and it's going to burn. It's as simple as that. We can try keeping it out, and all we do is we create more spectacular fires. And we've got a whole set of adaptations that suggest of what's happening. The first is mass suicide, and then serotiny, mimicry, and there's a few others which we won't have time for. Okay, so the first is resprouting. This is the obvious one. All plants resprout, really. Think about your garden plants. When you prune them, you cut them back into the old wood, and they all bounce back and come up refreshed and renewed. And the same happens with fire. After fire, all our resprouters come back refreshed and renewed. We saw them there. Some of them flower straight away. Some, like the King Project, take another 3-4 years to flower. And then they produce flowers and then go back dormant. But they all bounce back from the fire. And this is true of all ecosystems. And here is what the Americans call the war boom. And this is one of the big resprouters. Now, the interesting thing about the resprouters is that they have a very low death rate. If we measure their death rate in Fynbos, it's about 1 to 5% per fire cycle. And if we do the maths, and that means that this plant is probably between 200 and 400 years old, which means that some of these plants, ones growing on Table Mountain, were probably there looking down when Van Riebeeck landed. So these are old, and we can appreciate it for a bigger tree like that, but we tend to ignore it or overgloss it when we're talking about low shrubs like this, like the common sunshine cone bush or the eucalypt or the huari. These plants are also in the order of 200 to 400 years old, and were probably also there when Van Riebeeck came. Compared to those suburbs there, some of which are less than 20 years old, and we think we've been there forever. But the thing about Fynbos is that only 15 to 30% of the non-bulb flora, actually resprout. In other ecosystems, 90% of the plants, 99% of the plants resprout. And if you think about it, if you're going to be a forest tree and something comes and nibbles you, or if a branch falls down or breaks off, you need to regrow it. So you do need to resprout. But in Fynbos, 80% of the species don't even bother investing in the resources needed to recoppice or to resprout. They are killed. They are living to die. And that's what makes Fynbos so unique. It's not the resprouters which survive the fires. It's the other plants which actually die from the fire and get killed by the fire. And if you think about it, it has to be like that. It can't be any other way. Mass suicide is essential. We have to have a mass suicide. And it breaks down to this. If you are an ecosystem and you've got your plants growing and you want a fire and you want to have your babies survive in the post-fire environment, you have got to make sure that the succession doesn't go on any further, that other plants can't come in, that other plants can't take over and move on. You've got to kill them all. And the only way you can kill all the other plants in the succession is to die yourself by burning them up. And then after the fire, you can then germinate your plants and come up en masse. So you invest all your resources in producing seeds and in producing fuel. And when the fire comes, you kill everything and your seeds are there to come up. And that doesn't work in grasslands, it doesn't work in savannas, it doesn't work in forests, it doesn't work in the rest of the world. It's a Fynbos Mediterranean thing. So what we've got is this old Clemensian system where we have our disturbance going towards the climax. And if you want to engineer a fire to have a fire climax, you've got to make sure that when you burn, all these species are eliminated from the system. So you need a fire that will take you back and burn everything and stop the succession there so that you can keep your succession in the early stages of the sequence. And to do that, you need to make sure that when you burn, everything else burns with you and that nothing survives. And hence the mass suicide that's needed for Fynbos. And so what's unique about Fynbos is not the resprouting and surviving the fires, but all those species that burn up and make sure that nothing else survives the fire. Of course, there are nuances, and I wish I had lots more time for this talk. So we've got, and let's look in the rocky areas, because rocky areas are interesting because the fire is slowed down because of the rock, because there's less fuel and then other stuff. And so here we see some interesting strategies played out, which may be playing out there, but here fire dominates and it's much more difficult to study them or to understand them. But here we've got a slungbos, stevie, growing in this rocky outcrop. And what's interesting about stevie is it produces small little seeds and it drops them onto the ground so they lie on the ground. So if a fire comes through and it's a hot fire, those seeds will all be burnt and they'll die. So what this plant does is it retards the fire and slows down the fire. It doesn't stop the fire, but it slows it down so that it's cool. So the fire comes into a stevie patch and you have lots of smoke, but very little flame. And the fire moves through cool and the seed bank is maintained intact. And the other species are killed by the fire, but the seed allows, and we're going to have another patch of stevie coming in there after the fire. But we've also got other species that are fire promoters. And here is one of the buchus, the Cape May, and it's in this rocky outcrop and it's full of volatile oils. And it's going to explode when the fire gets in there, and it's going to carry the fire in there and create an incredibly hot fire in amongst these rocks. And it can do that because its seeds are carried underground by ants, and the seeds are safely underground where they're nice and deep. And it can burn up all the buchu, all the stevie, all the slungbos seeds, and it can make sure that the environment is perfect for its kids, which need the heat to germinate and to grow. So we've got this whole war between those species which are trying to get the fires cooler and those that are trying to get hotter. It's not just the passive thing of burning up. The plants are manipulating the fire. And we saw that at UCT. You don't want any of these around your buildings because they're desperate to try and get everything to burn, including your building. And it gets more involved than that. But this is our varboom again. And here we see it is a coppicer. It coppices from its stem. In fact, it's the only Fynbos plant that actually coppices from its stem. All the other ones, if they coppice, burn down to the ground, and they coppice from their ground, from underground and bulbs, or from bulbs. This is the only species that does it. And in fact, it turns out from DNA work, well, we used to think that this was the old primitive proteas, and that they started somewhere in tropical Africa and migrated down to the Cape and then exploded in the Cape in the spectacular diversity we see in Cape. But now with the DNA work, we know that that's not true. That the species always have been here in the Cape. The diversity has always been in the Cape. But the varboom developed this method of surviving in its epicormic buds Exactly how, we're not certain. But with this innovation, this allowed it to colonize the savannas and grasslands. And it's only during the Ice Age, from the Cape, from this lineage of epicormic resprouters, that proteas have been able to get and explode through tropical Africa and the African mountains and colonize Africa. So we have this great innovation. And the problem with this is that it can't have too hot a fire. If the fire is too hot, it will destroy the branches, it will kill the epicormic buds in here. So protein nitrogen needs a reasonably cool fire. But that's not going to happen if other proteas grow around it and take over. And I mentioned before earlier, remember that fire destroys all the pathogens. Well, by surviving as epicormic buds, protein nitrogen keeps some of its passengers. That's witch's broom. And you can see it attacks the plants, but a big plant like this is not going to be affected by a little bit of witch's broom. But the competitors, the gray proteas that grow with it, and which might grow dense enough to actually burn it and kill these plants, are actually killed by that parasite when they're young and seedlings. So by keeping the parasite in these populations and infecting the neighboring plants, they keep the densities of their competitors down. And so we have a whole COVID type warfare happening in the plants as well. It's not all passive, it's not all quiet and burning down. And we even see it on the biome level. So this is the keelworm. And if we go hiking here in the Garden Route National Park above Nature's Valley, you will see as you walk here that they're on the interface between the forest and the fynbos. We have these den stands of keelworm. And what the keelworm does is it tries to get the fire from the fynbos into the forest and to push the forest back. And of course, the forest resists and tries not to burn down, but it's the flammability of the keelworm and its long-lived seed banks, which can be 100 years in the soil, and they need heat to germinate. That allows the fynbos to start colonizing and pushing the forest back. So it's a dynamic system. It doesn't stay the same. Some fires will burn in, other fires, the forest will expand into the fynbos. But we have a whole biome boundary determined by species that are trying to push the fires in. And you all know Vigilia would be a lovely tree in the cities, except it only lives for 15 years. It only lives for one fire cycle. So you can't plant it in the cities. It doesn't live long enough. The other strategy is serotony. And this is where plants store the seeds in fire-safe cones. Now, serotony is very rare. You don't get it in savanna or grasslands. There is some serotony in succulent Karoo, but that's not for fire. That's storing the seeds in the plant for rain. And they only release the seeds after when it rains. In serotony and fynbos, it's a matter of having fire-safe cones and actually storing the seeds, not in the ground, but in the canopy of the plant in fire-safe cones. And we can have up to 6 years of seeds on the plants. And this occurs in the dominant species, and only the dominant species. And then we'll see why in a moment. So there's some of our proteas. There's a leucodendron with its cones. It's mainly proteas that are serotinous. We do have the Clan William cedar, that's also serotinous. So it also needs fire. It's also sitting there with its seeds waiting for the fire. And then a few other plants that do that. I showed you the erica that did it. Now, the problem with serotony is that you have to be robust. So you want the fire to come through and burn everything else, because you're now going to release your seeds into this post-fire environment. But you need to have your seeds high enough in the canopy so that the hot fire at the ground level doesn't kill and cook the seeds. And then also, as the fire burns, you don't want to drop these seeds into the firing mass. You've got to keep them up there. So you need to be strong enough to hold those seeds up above the fire and survive the fire at the same time as burning and killing everything else, and keeping those seeds safe. And then you keep the seeds in the plant, on the plant, for a week or two until all the rodents and birds are starved and have died. And then you release them en masse in huge quantities so that any rodents which did survive will be overwhelmed and your seedlings will have a chance to survive and will germinate with the next fire. Sorry, not the next fire, with the next rains. So when the rains come, the seeds will germinate. So this is just a horrendogram showing the population dynamics for serotinous species. And we'll start somewhere. Let's just start at a random point over there. There's our community. And then we have a fire, and the community can either get more or less. So they can either go to less or they can go to more. And what we seem to find is that if we have a hot summer fire, proteas will increase and increase and increase. And every time we have a hot or a summer fire, proteas love it and will get more and more. By contrast, if we burn in spring, which is not the ideal season, or if we have a cool fire, then the proteas don't recruit so well. And the theory is that if we have a fire in summer, say fire in February or March, the seeds are then released and they lie on the ground until the autumn rains in April. So they lie around for a month or two and then germinate. Whereas the spring fire, they released in, say, November, and they have to sit there for November, December, January, February, March, April, and then they germinate. So they're sitting there for a long time and they get predated and they die and they blow away and they cook in the hot ground. And so the populations tend to decline. So as a rule, populations under ideal fires increase, but we reach a stage where proteas get so dense that they actually can't make babies. They can't make flowers. They can't make seeds. And under these conditions, even with an ideal, perfect hot summer fire, the populations will crash to very low levels. So we have this interesting dynamic. And if you come into any one place, for any fire, you might be in a community that only has a couple of proteas, or that is dense with proteas. It's the same community, it's the same system, it's the same environment. It's just the fire dynamics of the stages of the community and that determine whether you have lots or little proteas. And this is what makes Fynbos so fun, in that you cannot predict what the next fire is going to bring. And this fire is going to give you a protea community. The next fire will give you in the same place an Erica community, and the next fire will give you a Restio community. And because of the dynamics of the way the system is playing out with the fire. Now, what happens after the fire? The seeds lie on the ground. How do they know when to germinate? Well, it's simple. When it's wet and when the temperature gets cold. The cold requirement is important because otherwise they might germinate after a summer storm. And in the summer storm, they'll die of the drought. So the rare summer storms need to be catered for. So the seeds have a simple requirement that when they're wet, when the temperature drops below a temperature, and it depends from species to species and from place to place, but about 9 degrees, they'll start germinating. And after a week or two, they'll start germinating and growing when it's wet. Now, the other strategy we have in Fynbos is mimicry, and this is seeds which are buried by the ants in the nests. And in the ants' nests, they are safe from predation, but the big questions are, how do they know when to germinate? And how long will they live in the seed bank? And this is just two proteas, Honorary and pincushion, which are two big genera which are exclusively mimicochorus. So the mimicochorus is quite simple. The plants produce these fruits, and leucospermum means white seed. There's our white seed, and the white on the outside of the seed is the ant fruit. And the ants will come and collect the seeds. They'll actually climb up the trees, climb up the plants, catch the fruit, throw it out, and then take it straight back into their nests. And in the nest, they'll eat off the white lysome, and then they've got a hard round nut which they can't move. So the seed is now in their nest, and it's safe in the nest from predation, safe from fire, and will wait there in the nest until the fire comes, and then it will germinate. And we have a whole set of species which disperse seeds. The bigger species bury them deeper. The smaller species bury them more shallow. And we have an alien species, the Argentinian ant, which comes through and it eats the seeds on the ground. It doesn't bury them all, and then they die because the rodents eat it or the fire kills them. So Argentinian ant invaders, bad news. So we have the same situation with our mimicochorus species and Therochorus, which are the ones dispersed by rodents, in that we have populations and they produce these large underground seed banks. And if we have a cool fire, then the plants die and disappear and have gone, but the seeds don't germinate. And so after the next fire, we don't have any plants. And this might happen a few times until we have a hot fire. And when we have a hot fire, they germinate. And now suddenly we have a population where previously there were none. We now have a nice healthy population of species of plants, and they produce more seeds in the bank. So normally with hot fires, the population just keeps on going and they stay there. But if we have a cool fire, we can have a situation where nothing comes up. How do they know when to germinate? Well, when there's nothing on top of the soil. And what happens then is that because there's no plants as a blanket, the sun bakes down on the soil and heats it up during the day. And then at night it gets cold because there's nothing to stop the heat from radiating out. So we're getting these cycles of hot and cold. And what these plants do is they need a situation where they need 10 to 14 cycles of this wet and cold going below a certain temperature. So it happens in winter, so it doesn't germinate in summer. And they have to be wet. And then after 10 to 14 cycles, they will start to germinate. And that is the essence of the story. But what's missing from it is that it needs a trigger. And one of those triggers is fire. Either the heat from the fire, or the smoke from the fire, or the charate, or the fact that the ants' nests die and the pH changes. And with 2,000 species using this strategy, there's a whole host of different mechanisms of how they germinate. I'd love to have at least half an hour to tell you the story of my meaties, Tokai. It's a really interesting story, but I don't. So I'll just quickly run through it. It was discovered by Stoko. That's not Stoko, who forgot where it was. It was rediscovered, but it was kept secret. Mari Vos came along and she needed a place to grow her proteas. So she grew a king protea stand for experiments, and she plowed up a piece of felt, which she got permission for, and she wiped out the only known colony of Maimetes Tokai. So that was it. Mari Vos wiped it out. It was extinct. She died, and it was still extinct. And that was the story. So we know from the history that the last plants to have flowered and set seed were in the 1950s. And that was it. When Peter Slingsby told me the story, we decided, well, why don't we actually go and burn the area again and see whether the seeds are still there in the soil and whether we can come and get them to come up. So we got forestry to burn. They were keen with the idea. They did the spectacular burn, started at 9, finished at 11, nice clean burn, perfect, and nothing happened. So we concluded that the species was extinct. And then in the year 2000, a really hot fire came through, and over New Year, and it burnt the area with a hot fire, and voila, 37 plants came up in the middle of Mari Vos' plot, which of course had long gone over because she'd moved on. And here we are at 5 years. You can see half the plants have died, but the others are nice and growing and flowering, and they're setting seeds and they're replenishing the seed bank. And in fact, since then, in year 2010, we had another fire, and they have bounced back again, another hot fire, wildfire. And that's when we realized that some of the species don't just want fire. They need hot fires. Fires in the middle of the fire season, the time of the year when humans do not want fires at all because they're totally uncontrollable. Now, how long do these seeds live for? Well, we can look at this from this story, in which were some seeds which were collected by Jan Teerlink in Cape Town in 1803, and he put it into his wallet. He then sailed to Netherlands, but because Netherlands was at war with the UK, he was captured and his packets were confiscated and were kept in the Tower of London so that they couldn't escape. And they then moved them to Chancery Lane in the National Archives. And then in 2005, Roelof van Gelder, who worked at the Millennium Seed Bank, discovered them in the archives, and they decided to germinate them, and voila, out came babies. So over 200 years stored in London, and the seeds were viable. So we now know that seeds live for a long time, and that there's a cache of seeds underground, so that if an unfavorable fire comes too frequently or at the wrong time of the year, there's a reserve of seeds that will survive the fire. And people are always talking about too frequent fires. What happens when there's too many fires? Well, the answer is that we'll lose the species that need longer period of time to flower. So if we burn every 2 years, well, 30% of the flora is safe because they're going to coppice, they're going to resprout. And if we burn every 5 years, then half the species are going to survive. They can cope with it. And if we burn every 8 years, then it's only 100 species out of 9,000 which need longer than that to survive. So too frequent fires are not the huge problem that people make out. And because as well, it changes in the landscape. So when you have lots of frequent fires, there are patches that don't burn, and then these species survive in the patches that don't burn. So it is dynamic, it's system, and a lot of the stories about too frequent fires are overblown. Yes, it is a problem, but it's not as bad as people make out. And then Jan Vlok argues that the opposite is true as well. So that 15 years is a tipping point, which is the average time. So when you have frequent fires, the resprouters dominate the system and they grow and proliferate. But if you allow it to go over 15 years, then the obligate long-lived species take over and they suppress and wipe out resprouters, which allows the other reseeders to grow in and take over and to grow up, and then the system is more dynamic. So how old you allow the veld to get determines on what species are going to be there after the fire. Okay, I'm almost finished. The question is, what about the animals? That's what you all want to know, isn't it, surely? Well, what about the animals? The important thing to remember, there's a Facebook, is that these animals don't live for long. They don't live for 15 years. What's a Facebook's lifespan? 6 to 10 years? This means that this Facebook cannot learn from its mother how to survive a fire. Its survival has to be totally instinctive. It has to know what to do and know where to go and know how to survive without ever having experienced it before. And anyone who doesn't know gets killed. So any species that can't cope with fire went extinct long time ago, millions of years ago. And the species we see around are those which are all adapted to fire and can cope with fire. And insects, well, exactly the same. They're the same thing. Everyone knows how bees, if you put smoke, they go calm. Well, if you put smoke in the veld, they all go straight to the hive, sit in the hive, and look after the hive, fan it if necessary, but go docile and calm and wait for the fire to go through before they come out again. What about the poor chameleons? They work so slowly, they can't escape. Well, they can move very fast when they want to. And what we think they do is that at the first whiff of smoke, they go down to the ground, find the mole holes and the mole rat holes and the mouse holes, and they go underground and they survive the fires underground. So even though they look like they're slow, they move it when they have to. And what about all the frogs and stuff? Well, the frogs and stuff are dormant in summer because it's hot and dry. They're underground. They don't even know about the fires. They're estivating, hibernating. They're not worried about the fires. The problem is when we burn after the rains, when they've come out, then we can kill them. They still got their holes to go in, but they then suffer from the fires. But during the fire season, during the summer fire season, they're dormant. They're perfectly safe. And even the birds don't breed during the fire season. So December, January, February is very low breeding season in terms of the birds in the Fynbos. They're not doing anything then. They start breeding with the rains. And then, of course, we have the tortoises. You're going to ask about the tortoises. And I'm afraid, repugnant as this may seem to you, tortoises are just glorified meat pies. They have chosen for when the fire comes to burn. Just like the plants, they're going to die. And what they do is that in spring, before the fire season, they will lay the eggs, 1 or 2 eggs underground, and the fire comes through and the adults get killed. And then in autumn, after the rains, the eggs hatch, and we've got our population restored, and the system continues as normal. So if you're going to go and rescue tortoises, please don't bring them back, because after the fire, the population will have restored itself. If you bring back the tortoises and release them there, you're going to be bringing in the diseases, you're going to be bringing in competition, and the poor babies won't survive. You'll be killing them by bringing in competition. So yes, if you're going to rescue tortoises, you need to give them away as pets or look after them in some other way. Okay, I'm almost finished. I just got to say here that if you think I've presented a coherent picture and that I know a lot, I'm afraid I don't. We know nothing. We've only just begun to scratch the surface. In 100 years' time, some botanist is going to sit over here and quote me and quote what I've just said and say how wrong I was. And here's just an example. 2016, this Restio has been found to dupe this dung beetle to bury its seeds so it'll be safe from the fire. And how does it do it? By pretending to be a Bontebok drop. So there's your Bontebok poop, and there is your dung beetle going and burying it. And only after he's buried it does he discover, or she discover, no, that's not a Bontebok drop. That is a seed, and the seed is safe underground waiting for the fire. So there's lots we don't know. A quarter of our Restios we can germinate, because they're spectacular plants, they're grown horticulturally. The other ones we don't know how to germinate. They come up after fire, but in the nursery we can't get the seeds to germinate. So there's lots we don't know. We've only scratched the surface. And I'm going to stop with a quote by Sir David Hutchins. He was made a sir, you'll see why in a moment. And he's from 1893, before our botanists got going. He was the British forester and he worked in the Cape and in the Highveld. And he said, great misapprehension prevails on the subject of fire, caused mainly by looking at it from the point of view of an inhabitant of Northern Europe. The veld fire here is not an incendiary disaster, but a natural process that usually is only dangerous when ignorantly interrupted or for some reason or other too long deferred. So we've known about how to manage fires for a long time. Every generation seems to try and reinvent the wheel and do it differently. So thank you very much. I hope you enjoyed it. I'd like to thank Mike for allowing me to use the pictures from the Cape of Flame. Unfortunately, the book is not available, but Mike assures me that for the 2030 fire, he is ready. And they will have a book out. And again, they will use the proceeds from the book to support the groups involved with Table Mountain, including the Honorary Rangers. And here are the links I told you about in Natasha and William Bond's video. And yeah, please go look at William's video. And I hope you enjoyed the talk, and I'm quite willing to answer any questions you might have.